Hi, welcome to this talk on the rapid determination of Scoville Heat Units of chili-based products. So I will be talking today about a paradigm shift where rather than sort of testing using large, expensive third-party instruments, we can actually do the rapid determination of food ingredients quality using handheld instruments. Now, the technology I will be talking about originated in the University of Oxford, but I will talk about the history before this, and then the development, and also the science that we're actually using. And then I'll also do a demonstration as well as part of this talk. So just to say, my name is Martin Peacock. I was one of the founders, or I am one of the founders at a company called Zimmer and Peacock. We were launched in 2014. We are what is called ISO 13485. So a lot of what we do is contract development, contract manufacture of electrochemical biosensors. And that will become relevant as this talk progresses. At ZEP, we're quite a large team. What we're talking about today will involve chemistry, food technology, electronics, mechanical, cloud technology, app development, quality systems. So it needs quite a large team in order to, and diverse team and very educated team in order to work on a kind of technology that we're talking about today. Just so I can sort of position this, what I will be talking about is actually a technology like this that uses sensors in order to measure the hotness of products such as chili oils, chilies, chili flakes, for example, chili powders. So I will be also purees, I should say purees like this, and I should also say, you know, it can be also be used for things like sauces as well. But anyway, I'll come on to that as I go through the presentation today. So, for example, if you're a quality manager or manufacturer of products that use things like chili powders, those chili powders contain a group of molecules called capsaicins. Now, these capsaicins, when somebody eats a product, there's a receptor in the mouth called TRPV1, transient receptor potential valenoid 1, and this receptor is what binds with capsaicin, and then you get this stimulation of this heat. Now, in order to kind of have a reproducible product, you kind of have to understand how much capsaicin is in your incoming material or how much capsaicin is in your actual product. If that's a variable, then the consumer's experience will also be variable. Sometimes you'll have complaints it was too mild, and sometimes you'll have complaints it was too hot. And it's really because when you're dealing with things like chilies and you're dealing with things like chili powders or chili flakes or even, you know, oils, etc., the amount of capsaicin in them is actually a variable. So it does lead then to a kind of quality control concern, and that's what we'll be addressing today. Now, the first attempts at objectively quantifying the hotness of chili products was invented by a guy called Wilbur Scoville in 1912. He invented an organoleptic test where you would essentially dilute chili products until you could no longer taste the hotness in there, and he would do this using large panels. It's very time consuming. It requires a lot of people, and it's not, you know, super, let's say, objective. Now, in about 1995, high-performance liquid chromatography started to come into this testing. The AOAC invented a method called 99.5.03. Some of you may have HPLC testing done by a method called ASTA 21.3. That's the American Spice Trade Association's method 21.3. AOAC 995.03 and ASTA 21.3. These are basically the same test, and they both use high-performance liquid chromatography. And as I say, this started at approximately 1995. Now, the problem that we have with this high-performance liquid chromatography is that there can be you, who is the manufacturer of some product, or you're trading in spices, or spices are coming into your process and you're really not sure how hot they actually are. At the moment, the traditional workflow would be actually you would take a sample, You would send that sample to a laboratory. The laboratory would start to do a chemical extraction so they could take the capsaicin out of your sample. They would do a dilution. They would put it onto what's called the HPLC, the High-Performance Liquid Chromatography system. That would run, and the instrument would give out a signal called a chromatogram, or a data output called a chromatogram. Now this chromatogram is the area under here is the amount of capsaicin actually in the sample. But that's not the end of the journey then, because periodically they would have to actually calibrate their system to convert area under curve into Scoville Heat Units. And then eventually that would get reported back to you. You can appreciate that you've got transportation, processing, experiment itself, calibration, and then you have to receive the data as well. So all of that really leads to a slow process. It's expensive, it's slow, it means under testing. You can't afford either the time or the money to do a lot of testing. So in fact, it leads to people not doing as much testing as otherwise would be required for process control. And there's really no transparency on this. And what I mean by no transparency, people take the certificates of analysis or the results that come from these labs at face value. There's no kind of understanding of whether they're actually accurate or precise. You just get the certificate and that's essentially the end of the conversation. So it's not a very, let's say, satisfactory conversation. Now, what I'm going to talk about now is technology that originated in the University of Oxford. So again, this is not, this technology hit the kind of public consciousness in about 2008. So don't forget, I'm talking today in 2024. So this was 16 years ago that this started. I've got children that are younger than this. Now, Professor Richard Compton was the professor at Oxford who originally developed the electrochemical assay. So that he both published the paper, but also they did a patent as well. And it was that patent that Zimmer and Peacock have a license. So you'll actually find out that this chili sensor, now we've had this license for a number of years, since about 2018. And we've actually been through a generation 1 product, a generation 2 product. With products, the longer you have them, you use them, clients use them, you learn lessons, you make improvements, etc. So over the years now, we've even gone through a generation 3 product, and then at the end of 2023 and into 2024, we've now been using the FoodSense generation 4. Now I have a FoodSense generation 4 in front of me, and I will be doing a test very shortly, actually testing a chili product. But let me go back to these slides so you will see this used for real. Now what Richard was doing in that original paper was taking what we call electrodes and putting a sample on. Now the sample size that we use today is actually 50 microliters. So we do not require a lot of sample in order to test a chili product. So what I will do is I just want to go here again. I'll just show you very quickly that what Richard was actually doing was testing these samples by a technique called cyclovoltammetry. Now, cyclovoltammetry is really a lecture in itself, so I will have to do a lot of summarizing, but I just want to state that that's what he's doing, and I will talk about it now. So capsaicin is the molecule of interest. We add it to these sensors using a pipette, and we add 50 microliters to it. Now, the technique that's actually running on the instrument is something, as I say, called cyclovoltammetry. So cyclovoltammetry has a very distinctive sort of shape, or at least when it's got capsaicin rather. We get these peaks. These peaks are the fingerprint for the capsaicin molecule. We got an oxidation, so we got what we call a peak 1, we got a peak 2, and if I just wait a short while now, we'll get a peak 3. And it's these 3 peaks that say this is definitely capsaicin. So there's our peak 3. Because this is a talk about the science of this, I just want to talk about where these peaks are coming from. So we have this 50 microliter sample. It contains capsaicin. The first thing that happens is the FoodSense Generation 4 is applying a voltage, and we actually get an oxidation of capsaicin. So capsaicin is oxidized. If you just look at where this red box is, it undergoes what's called an oxidation. I know I'm getting into chemistry here, but it's lost an electron. The electron is shown as a current, and in the cycle of voltammetry, we get this peak. We call it peak 1, and that's the first indicator that this is capsaicin. So we can both qualify that it's capsaicin, but actually also the peak height and the area under the curves tells us how much capsaicin is actually in there. So it's both qualitative, yes, this is capsaicin, and it was also quantitative, because if the peak is large, it's then there's a lot of capsaicin, and if it's half the height, then it's half the capsaicin. So the peak heights are proportional to how much capsaicin is actually in there. Now, as part of the analysis, this molecule that we've just oxidized, this capsaicin that we've just oxidized, undergoes a chemical reaction. It's called hydrolysis. Hydro means water, and lysis means bond splitting. So we break a bond with a molecule of water, and we form a new molecule, which is in a group of molecules called quinones. Now this will lead to what we call peak 2. So I will analyze that now. So we have this quinone that was formed from the hydrolysis of the oxidized capsaicin. That quinone is reduced, and we get a quinol, and it is this quinol then that leads to peak 2. So when you look at this cycle of voltammetry at the moment, you will see that we have what we call a peak 1, and then we have a peak 2, and that's what's giving the second indication that it's actually capsaicin. Now there's also something that we call a peak 3 as well. I just want to say, by the way, that I just need to remove my my image from here. So it's actually the peak 2 that is the second indicator that this is capsaicin. I do want to say that this quinone is reduced to a quinol, and it sticks to the surface of the electrode, and in doing so it actually means, unfortunately, you can't reuse the sensors because this quinol is irreversibly bound. If you try reusing a sensor, all you're going to do is carry capsaicin from the last sample into the new test, and the situation will just get essentially worse and worse as you reuse the sensor. So you cannot reuse the sensors because the capsaicin ends up being irreversibly bound to the sensor. With peak, the next thing that happens then is we've got this quinol bound to our surface, and actually that is subsequently oxidized to give us a quinone molecule. So we get peak 1, then we get the reduction of the quinone to quinol in what we call peak 2, and now the quinol is bound to the surface, and we get a new peak called peak 3, which is giving us the third indication that this really is capsaicin. Now, coming away from the science a little bit and back to the practicalities of actually using this, we have done a lot of testing over the years. We've tested, in the US, people are very keen on spicy mayonnaises. So we have definitely tested those. We've tested chili oils. We've tested hot chili sauces. We've tested chili purees. We've tested chili powders. We've also tested olea resins. There's been a couple of academic groups, and we do it as well, of also testing fresh chilies and also dried chilies like this as well. So there's also been a lot, and that's one of the good things about the instrument. It's very flexible in terms of the kind of sample types it can actually deal with. If you're interested in this technology, it's probably worth knowing that it's already distributed. There's an app involved in this. You'll see that app in the demonstration that I'll do shortly, but the app is available on the Google Play Store, and you'll also see that this app is also available on the Apple App Store. And you will also see when I do my demonstration that the app is in communication with a cloud system called Julie. So every time we do a test, please understand that the result will appear on your phone, but also the raw signal is saved up into the cloud. The raw signal, the date, the time, and the operator. So that's a very good way of having traceability on the test. As I say here, I'll do a quick demonstration. So you take one of the chili sensors, you put it in here. I'm testing something a little bit unusual today because we just had a recent inquiry, and somebody actually wants to test one of these chili infused vodkas. So I've got a sample of this vodka here. It's probably worth just saying that this I'll be controlling the FoodSense Generation 4 actually through the app. So I will be doing that now. So let me just, in fact, what I'll just do is I'm just going to give this a name. So let me just give it a quick name now, and I will put that name in like that. I'm just going to put the sample 50 microliters onto the sensor. So let me just do that very quickly. There we are. The sample is now on. And what I will now do is go to assay. One of the things that's really great about this is actually the speed, essentially, of the system. What I mean by that is, you know, we can prepare samples quite quickly. We only use 50 microliters. You can just put 50 microliters onto the system. It's very easy to set up. No calibrations required. Now there's a progress bar on the app, and the app is essentially, how do I say this? The app is driving the meter. The app will get the result back from the meter, and I have a result. So what I'm going to do now is I'm going to just change my screen for a second. So you will get a result on your phone. So you'll get, for example, this vodka is quite mild. It's only 1080 Scoville Heat Units. And it also says something like upload complete. So what I'm going to do now is I'm just going to click done. Right, so it's gone back to the home screen. But I just want to share with you my screen, which I will do here. And here is my screen. And in fact, my data is already uploaded. So the reason I was but I was talking about the electrochemical paper from the University of Oxford is, in fact, in the cloud, we save the file name, the date, when was this experiment, let's say, done, the time that this experiment was done, who did the experiment, and then the raw signal itself. So I was mentioning that, you know, in fact, there's 1, 2, 3 peaks, and we can see them in our data. So that's a really kind of, how do I say that? A really useful sort of, the fact is, if you're ever challenged about where this number comes from, we always have the evidence of exactly where this actual number came from. So it's quick, it's easy to do, there's no setup, there's no calibration, and you get all the details about who did it, when they did it, and what the real raw signal was. And as I say, I actually also get the Scoville Heat Unit also saved up in the cloud as well. Hopefully that demonstration kind of gave you an indication of the entire system. So what I want to do now is just essentially do a quick summary. So the problem that we're trying to fix is that the only objective way outside of using the FoodSense Generation 4 is to use HPLC, but it is expensive, it is slow, it does lead to under-testing, and there's certainly no transparency about it. But of course, what I've demonstrated here, and this technology that was originally invented in the University of Oxford 16 years ago now, is actually we can do a rapid qualification. You know, is there capsaicin in that product, and how much capsaicin is in that product, and then deliver it as a Scoville Heat Unit. So if you've got any questions to me regarding this, please don't hesitate to reach out to us. Okay, thanks very much.